next in-person plenary is doesn't need a lot of introduction to this crowd. I think a lot of you know him from his earlier careers. He's also a generous patron of this conference and one of our plenary speakers, Sonny White. Sonny, take it away.
Hey, thank you. Thank you, Stephen. Appreciate the kind intro. My name is Sonny White. I'm the Director of Advanced Research and Development at Limitless Space Institute. I want to talk to you guys a little bit about who we are and what we're doing in this grand endeavor. Our mission is to inspire and educate the next generation to travel beyond our solar system and to support the research and development of enabling technologies. Our big, hairy, audacious goal, the A actually usually means something else, but that's the polite chart, is to enable interstellar travel by the turn of the century. And that is definitely not an easy task, as everyone in here knows, and a lot of the talks have highlighted over the last couple of days. When we think about space exploration today, especially like human space exploration, we're only now just thinking about trying to send humans back to the surface of the moon with Project Artemis. In terms of robotic stuff, we have a lunar rover, sorry, not a lunar rover, a rover on the surface of Mars that's exploring the Martian surface with a little drone that's along with it. But when you talk about trying to send human beings into the outer solar system and beyond, that's very, very different. And just to kind of articulate that real quickly with a simple example, if we wanted to send human beings to Saturn in 200 days, the amount of energy that's necessary to make something like that possible is an order of magnitude more energy than it takes to get a payload from the surface of the Earth to low Earth orbit. So chemical propulsion cannot close that type of an architecture. And a lot of you already know that. But what are we supposed to do? How can we make something like that close if chemical propulsion can't do that for us? This is kind of our capability chart. It is a simple distillation of a very complicated subject, primarily with a focus of sending larger payloads. So there are other ways to do things with smaller payloads. But at LSI, we tend to be more focused on the larger payload approaches. So in the context of what we know on the left of both physics and engineering, we could potentially employ an architecture based on nuclear electric propulsion to send human beings to every destination in the solar system. This concept is well understood. It's explored in the literature. Certainly it's within the realm of what we know how to do, both in terms of an engineering and a physics perspective. If you talk about human beings, we're talking of power levels that are measured in megawatts. And to kind of put that in perspective, right, 2 megawatts is when you've sat at a railroad crossing and watched the locomotives go by, each individual locomotive is roughly about 2 megawatts electric power. That's what it's usually processing when it's doing its work. So that would potentially enable human exploration of the solar system. It might enable interstellar precursors, but it's not going to enable interstellar in a practical sense. NEP still might take the better fraction of 1,000 years to get to another star system. If we want to do interstellar with large payloads, right, we could potentially move a little bit into the unknown in the context of engineering at least. The physics is well understood, but we could engage fusion propulsion. You could potentially look at fusion electric propulsion, where you've got a fusion reactor that just replaces the uranium reactor, but more than likely you're going to do direct fusion drive. And you've seen several concepts that people have talked about over the last couple of days. Now, the power levels for this are going to be considerably higher than what we would anticipate with a nuclear electric propulsion system. Certainly, it's going to enable faster human exploration of the outer solar system. And for the handful of people that may watch the TV show Expanse, that's their propulsion, choice of propulsion for the TV show. But more importantly, fusion would enable us to send something to a nearby star system, but it's still going to take probably 100 years to do that. If we want to send a large payload to another star system in a fraction of a human lifetime, we kind of have to look to the frontiers of physics for ways to maybe do that, or bring some new ideas to the table, or maybe we could do something that we currently can't think of today. If you think of physics as a Venn diagram in terms of what we know, there are 2 circles on this Venn diagram, and they kind of touch at one tangent point between those 2 circles. In one circle is the word quantum mechanics, and that is the standard model of the microscopic world, and that helps us understand how the microscopic world works. We have transistors, we have cell phones. The entire digital age is built on that understanding of physics. In the other circle, we would have the words general relativity. And that represents our understanding of the macroscopic world. How do the stars move? How did the cosmos expand? But more importantly, we have highly precise global positioning satellites because the satellites have to make corrections for general relativistic issues and special relativistic issues. So the atomic clocks can accurately locate you when you're using your cell phone to go navigate to meet a friend. So just that understanding of physics affects our life every single day. But because those two circles don't fully overlap, we know that there is a more generalized understanding that we have yet to figure out. And so maybe in the process of trying to figure out the things that connect those two models, or maybe a more generalized framework that helps us develop a deeper understanding of something, maybe we can figure out ways of pushing off of space-time itself, whatever it's made of, or the quantum vacuum, whatever it's made of. We know that wormholes and space warps are mathematically possible. We heard a neat talk on that yesterday, but we don't exactly know what to build to make something like that manifest reality, if you will. So maybe working on the frontiers of physics, we could find some new ways to do things that might enable that. So at Limitless Space Institute, we are a doing organization. We are conducting research internally. Currently, we're funded by DARPA Defense Science Office, working on a frontiers of physics approach, kind of fits into that third swim lane. I'll talk just a little bit more about that in a second. We also fund research externally. We commissioned a program called Interstellar Initiative Grants in the summer of last year. We got proposals from all over the globe, and we picked 9 different performers to conduct research in several areas. I'll highlight each one of them with just a quick overview chart. We sponsor research with university partnerships. Currently, we're partnered with Texas A&M, working on a compact nuclear reactor in the 1 to 10 megawatt electric range. I'll talk just a little bit more about that in a second. And then we also do student programs. We partnered with the Initiative for Interstellar Studies to develop a week-long class on interstellar studies. And we taught that class this summer. We'll probably teach another class again next summer. Again, probably partnering with I4IAS. We always continually do education outreach, doing lots of talks with students at different locations. We may also be starting up some fellowship and scholarship programs in the near future as well. This is the NASCAR chart. This shows all the organizations that we have formal agreements with and have conducted work with and are continuing to work with. We have several more that are in work right now. We've only been doing this for just a little over a year and a half, so we're definitely moving as quickly as we can. There's a lot of people that want to engage in this, and we want to engage with them. So if you've got some things you've been thinking about, feel free to reach out to us. And we will probably be doing another Interstellar Initiative Grants solicitation in the summer of 2022 as well. Just to quickly highlight the work we're doing internally, working on something we call our dynamic vacuum model. This is something we've been working on for about 10 years, trying to manufacture some customized Casimir cavities that you can see on the chart there, and then studying how the quantum vacuum is predicted to respond to this customized topology that we're working on. So it's definitely 6.1 basic research, but there are some potential technological applications if we can continue to show interesting results in the lab. There may be some power implications for providing small amounts of power for, in DARPA's perspective, remote sensors. It may provide an ability to increase the magnitude of something we call negative vacuum energy density. That's something that's kind of critical for the idea of a space warp. There may be some communications and sensors applications of this work, and it might just possibly also be able to generate a modest amount of thrust. So a lot of computational work that we do here, a lot of nanofabrication. We're doing this in partnership with Texas A&M, using their nanofabrication facilities there. And then Isentis is using the nanofabrication facilities up at MIT and Harvard to help us try and figure out how to make these things. Just a quick thing to talk about the value of doing fundamental research. We had a completely unanticipated find as a result of studying these custom Casimir cavities. Let me pop back here just a second. If you look at the scanning electron microscope picture that has kind of an overlay of how the quantum vacuum energy density is predicted to respond to the presence of the pillar in between the two plates. This shows that, the top picture shows that, that plot. And so you've got that prismatic cylinder that comes in and out of the page, and then there's walls on either side that come up. You can see there's some increased magnitude of negative vacuum energy density, and this two-dimensional section cut looks qualitatively similar to what's required from the Alcubierre warp metric. And so you see there's a picture of the York time. That's the expansion and contraction field for the idea of a space warp. And then there's a little cartoon spacecraft kind of interposed on that to show you how that connects with the field, if you will. And that gray ring that goes around the spacecraft is what has to be something that generates the negative vacuum energy density. But the problem is this is the top picture is prismatic and the bottom picture is toroidal. So we did a specific model where we created a 1 micrometer diameter sphere in the middle of a 4 micrometer diameter cylinder and did the analysis and showed that the prediction of the negative vacuum energy density to the presence of those structures basically matches the Alcubierre warp requirement. Now this says that this is potentially, if you can build something like this and metalize it, it will generate a nanoscale warp bubble, a real nanoscale warp bubble. This is published in EPJC, so you can go look at all the work that we did and take a look at it. Now, the one thing I do want to say, don't get excited. This is not going to go anywhere. It's not going to do anything. But just as a matter of precedence, to me as a scientist, it's just interesting to think that we can potentially propose to the technical community that we can manufacture something that might generate a real nanoscale warp bubble. I think it'll have optical properties that are interesting long before we do anything else. So I just want to highlight the I2 grants performers. As I said, this is we commissioned this in the summer of last year. This is something we want to do every 2 years. It's going to be a 12-month period of performance. This is, if you want to think about this, it's like a NIAC with a focus on advanced power and propulsion, if you will. We're doing this in cooperation with Texas A&M and breakthrough initiatives. We have 2 different categories of awards that we gave out. We have a theoretical focus grant we call a tactical grant, and that's up to 100K for 12 months worth of work. And then we have a strategic grant, which can be up to 250K for 12 months worth of work. And we anticipate that has to be coupled with some type of experimental work as well. We announced the award winners on September 1st. And I'll run through the different grant winners here in just a second. But just to say before I go through them, we will be doing the finale of the grant performance work on October 14th. We have a Zoom webinar for that, so if you're interested, shoot us an email at Limitless Space Institute. We'll add you to that distribution. We're also going to live stream it on YouTube, so you can also watch it that way. And then if you have a schedule constraint, we intend to upload everything, so you can always view it at your convenience. Just to cruise through the grant winners, we've got Professor Phil Lubin at UC Santa Barbara, working on beamed energy propulsion. The work that we're paying for is to take some of the stuff that he's done a really good job in the lab and move it into the field and have some sources remotely located from a cooperative target and go through and demonstrate the ability for the two pieces of the system to lock and beam power from the source to the collector. We picked Professor Richard Norty at Delft University of Technology, doing some work on relativistic compatible solar sails, if you will. In breakthrough starshot, that sail has to accelerate to a good fraction of the speed of light, but it has to be highly reflective over that entire range of acceleration. And so the perception of the wavelength of the ground laser is going to change. And so the work he's doing is studying the different types of topological structures that he can make to maintain the high reflectiveness of the solar sail material over that full acceleration range. So you see some scanning electron microscope pictures of some of the things that they're doing there. We've got 4 fusion propulsion teams that we're funding. One is Professor Ray Sedgwick at University of Maryland. This is a very early concept, DT plasma. He's got an E cross B shear flow stabilization scheme that he's trying to use. And so we're paying for the development of the model to take it to the next level of fidelity to see if it still continues to predict the ability to generate the fusion propulsion performance that he wants to see. We're funding Professor Jason Casabry at University of Alabama, Huntsville. He's doing some work on pulsed break-even fusion. They have some equipment in the lab that allows them to do very high energy pulses into targets. And so you see a couple of pictures of targets there. And so they want to go through and explore. You see that puddle plot on the bottom left. There's a blue area and a yellow area. And so they want to figure out how close can they get to the transition from the blue to the yellow, because that's where the coefficient of performance, physics coefficient of performance goes greater than 1. We're funding Kelvin Long at the Interstellar Research Center to do some detailed work on a code to analyze inertial confinement fusion. We want to go through and study some of the historical concepts that are in the literature, and then use this to look at some of the future concepts as well. So he'll be doing that work for us. And then, of course, you heard from Helicity Space yesterday. Alan Stern was here. We're funding them to mature a piece of their design. We're funding the work on the peristaltic magnetic nozzle. And so that's the part that does, after the plectonemes combine, it further compresses the plasma using a peristaltic compression process to increase the physics coefficient of performance. And he's doing that in cooperation with Caltech, University of Maryland, Baltimore County. We have two teams working on what I would call a space drive. One is Professor John Bush at MIT. This is a pilot wave model that he's been working on for a number of years. It's called, in his parlance, a hydrodynamic quantum field theory. And so we're paying to mature the model into a three-dimensional model, and in the process trying to figure out are the ways that one could potentially generate a force by pushing off of this quantum vacuum field, and what could the magnitude of it be. We're funding Charles Chase at UNLAB and Professor Yuval Dagan at Technion Israel Institute of Technology, and the process of assessing some asymmetric potentials, specifically as they might exist in a resonant tunneling diode. When they integrate the vacuum fluctuations on either side of this potential, it suggests that there should be a non-zero force across the interface. And so they're going through and doing the models based on what they think they can manufacture, and maybe in some future work, they may actually try and make some of these things and test them in the lab. And finally, on the I² grants class, we have Professor Remo Guerantini at University of Bergamo, along with Professor Piero Niccolini at Frankfurt Institute for Advanced Studies, doing some work to try and optimize some of the mathematics of a traversable wormhole, and also looking at some custom Casimir cavity configurations, coupled with maybe using some superconducting materials to see if they can improve what's necessary to make something like this work. And then, as I said, we have a university partnership with Texas A&M to work on in this case, a terrestrial nuclear reactor that's 1 to 10 megawatt electric that fits in a 40-foot Connex container. We're doing this very purposefully to align with the DoD Pele program. We want to try and go through and show that you can have all the requirements that Project Pele has, and you can add a few additional requirements and have a reactor that is about 60% common with what a spaceflight reactor might be. We're trying to tell a story with government stakeholders that with some additional modifications of requirements, we can maybe make the large amounts of DDTD money be multi-purposed, if you will. All right, so there's my contact information. If you guys want to reach out for anything, let me know. And that's everything I had. I'll take any questions if anybody has any.
Thank you, Sonny. We have a couple of somewhat related questions. What would be the best way for students interested in working on LSI-funded projects to get involved?
What would be the best way for students that are interested in some of our projects to get involved? I think the first thing is to definitely reach out to us, so that we need to know you're there and that you have interest, number one. Number two, then maybe we can find ways to connect you with people that might be in your geography, or we could try and work to find people at your university that may have interest. Because a lot of times when you think about working on a master's, you do that with cooperation with a professor somewhere. And so let's maybe dialogue to see if we can't connect the dots there. And then we do have internships in the lab. And then of course we have existing programs as well. So there may be opportunities for overlap there.
Thank you. When will information on the fellowships and scholarships provided by LSI be available?
So the fellowships and scholarships, that's in work. As soon as we get that done and better defined, we'll try and put some of that stuff out there to provide the opportunities, right? So those will also be a competitive process, just like I² grants was. We did the I² grants review process was run basically identical to how NIAC runs its selection process.
Thank you.